Okay, so right now we're going to take a more quantitative look at the relationship between concentration and rate, or speed of a reaction. And to do that, we use something called a rate law, or sometimes known as a rate expression. A rate expression. So, a rate law relates the rate of reaction to the concentration of reactants. So the first key about a rate law is we're only ever looking at reactants. So when I look at my generic example, you'll notice we don't have generic products, because the rate, when we examine the rate with a rate law, we're not worried about how fast the products are being produced, because we can always go back and figure that out based on what's happening with the reactants. And you'll notice when I have this generic reaction, the rate law, or the rate expression, looks like this. So the rate of reaction is equal to K, which is called a rate law constant. And that is specific to each reaction, and also at a given temperature, because as temperature changes, so does rate. So the rate law constant is specific to a reaction at a given temperature, and that is multiplied by the concentration of each reactant. You'll notice, remember, square brackets mean molar concentration. Molar concentration of A, molar concentration of B, molar concentration of C, raised to some power. Now, the exponent that the concentration is raised to is not the same necessarily. It might be the same, it might not be the same as the coefficients in the balanced chemical reaction. So that's why you don't see A, B, and C over there. These exponents are referred to as orders for the reaction. And they must always, always be experimentally determined. You cannot just look at an overall chemical reaction and go, oh, I know what the order is. You must have experimental data to figure out the exponent for each of those concentrations. The exponents can be small whole numbers, or they can be fractions. We will not deal with anything with fractions. They're typically small whole numbers, 0, 1, 2, maybe 3. 3 is kind of rare. Anything above 3 is very rare, for reasons we'll get into when we start looking at what's happening on a molecular level. So, if we determine that the exponent is 1, we say the reaction is first order with respect to A. If we determine that the exponent is 2, then we say the reaction is second order. If we determine that it's 3, we say the reaction is third order. If the exponent is 0, then it would be, so if I had rate equals K times the concentration of A to the 0 power, we would say the reaction is 0 order. Now, this is a special case, because if I look at the math behind this, first order means raised to the first power, so rate and concentration are directly related. And the second and third order were raised to a power, so there's an exponential relationship between rate and concentration. Anything raised to the 0 power equals 1. So in a 0 order reaction, that tells me that rate is independent of concentration. Because anything raised to the 0 power mathematically is 1. So no matter what the concentration is for a given reaction, at a given temperature, if the reaction is 0 order, then that reaction basically runs independently of the initial concentration of anything. That's pretty rare. It does happen, but that is kind of rare. So in the next video, part 2 of this, we'll look at what kind of experimental data we need to determine the order and then ultimately determine the rate law for a reaction.